Hi, everybody, it's Professor Mitchell. We're continuing with Chapter 10. Today we're looking at Section 10.3, Simplifying Radical Expressions. In this section, we'll use the product rule for radicals, the quotient rule for radicals, we'll simplify radicals, and then we'll look at the distance and midpoint formulas. And we're still working on SLOB. All right, so the first thing that I would like you to think about, pause the video, first figure out what is the square root of 9 times the square root of 4, and then figure out what is the square root of 9 times 4. All right, pause the video, figure that out, come back and compare notes. All right, here we go. So the square root of 9 times the square root of 4, we would evaluate each square root separately. The square root of 9 is 3. The square root of 4 is 2. 3 times 2 is 6. On the other hand, 9 times 4 is 36. And the square root of 36 is 6. So notice those two came out to the same answer. Now that could be a fluke. I'm here to tell you that is not a fluke. All right. Radicals work that way with multiplication. And that gives us what's called the product rule for radicals. So if the nth root of A and the nth root of B are real numbers, then the nth root of A times the nth root of B will always equal the nth root of A times B. So you're going to see a few different examples of how we're going to use that. But first, let's look at this. So once again, I want you to pause the video, first figure out what is the square root of 64 divided by the square root of 4, and then figure out what is the square root of the quotient 64 over 4. All right, here we go. The square root of 64 is 8. The square root of 4 is 2. 8 divided by 2 is 4. 64 divided by 4 is 16. Square root of 16 is 4. So those also come out to be the same. Again, that could be a fluke. Again, that is not a fluke. It's always going to work that way. And that's called the quotient rule for radicals. So again, as long as the nth root of A and the nth root of B are real numbers, then the nth root of A over B will always equal the nth root of A divided by the nth root of B. All right, so for the first couple of examples, we're going to use the product rule to do these two problems, and then we're going to use the quotient rule to do the next two. So switching over to the tablet. We are going to start with the fourth root of 27 times the fourth root of 3. So we just learned that the fourth root of 27 times the fourth root of 3 is equal to the fourth root of 27 times 3. And the reason I'm so excited about that is because I have no idea what the fourth root of 27 is, and I have no idea what the fourth root of 3 is, but 27 times 3 is 81, and I do know the fourth root of 81. The fourth root of 81 is 3. Okay. So one thing the product rule does, it allows you to evaluate radical expressions that I would not be able to evaluate if I didn't know the product rule, because again, I have no idea what the fourth root of 27 is, and I have no idea what the fourth root of 3 is. So I can't evaluate those separately. All right, and I just remembered that especially when I have more than one problem written on the same screen, I like to use a different color for the solution. But actually this one's quite a bit shorter. So we have the square root of 6 over m times the square root of 5 over n. According to the product rule, that's going to equal the square root of 6 over m times 5 over n. By the way, there is an unwritten assumption here. I think the safest way to say it is just to say that all variables represent positive real numbers, okay? Because then not only do we have to not have to worry about any of these radicals not being real numbers, but we also don't have to worry about that annoying thing from section 10.1 where sometimes you have to use the absolute value. So as I was getting this ready, I noticed that they didn't always write that in the directions. So I think it's okay whenever you're doing a radical problem involving variables. I think it's always okay to assume that the variable represents a positive number unless the directions say that it can be any real number, okay? And that usually doesn't happen. Okay, back to this. 6 times 5 is 30. M times n is mn. And that is really all we can do with that because I don't know anything about m or n, all right? So we would just leave it like that. All right, and then we had the quotient rule problem. It said use the quotient rule to simplify these expressions, starting with the fourth root of y over 81x to the fourth. So first we're going to use the quotient rule to separate the radicals, put one radical on top, put one radical on the bottom. Okay, now the fourth root of y, I can't do anything with that. That's just the fourth root of y. However, I do know the fourth root of 81x to the fourth. Let's do a quick little review. I think that was in the last section. Or no, it was in section 10.1. The fourth root of 81x to the fourth is a mystery expression such that when you fourth power it, you get 81x to the fourth. Well, the number part of that would be 3. And the variable part of that would just be x, right? And that's why the fourth root of 81x to the fourth is 3x. So the answer they're looking for here is the fourth root of y over 3x. All right, next we have negative cube root of 64a over b to the 9th. This negative sign is just going to come along for the ride. I don't think we're ever going to do anything with it in this problem. Let's put this cube root on top. Put the cube root on the bottom. Okay, now in this problem, I have to be careful. Let's deal with the denominator first. The cube root of b to the 9th is b to the 3rd. So take a minute if you need it to think about why that is. Okay, we've talked about it a couple times before. All right, it's because mystery expression, where should I do this? I'll do it up here. Mystery expression cubed equals b to the 9th. That mystery expression would have to be b to the 3rd because 3 times 3 is 9. Now, where you have to be careful is in the numerator. All right, you might be tempted to say that the cube root of 64a is 4a. Do you see the problem with that? That would only work if it was the cube root of 64a to the 3rd. All right, so actually what we have to do with this technically is separate it into two radicals. So let's put the cube root of 64 times the cube root of a. All right, and then unfortunately, all I can say about this is that it is negative 4 times the cube root of a. Remember, make a nice clear separation between that 4 and that radical over b to the 3rd. So part of it is stuck inside the radical. All right, let's see what we have next. All right, so that brings us to simplifying radicals. First thing I want to say is that simplify does not mean approximate. So for example, you see in the first problem, I'm going to ask you to simplify the square root of 27. That does not mean ask the calculator what's the square root of 27, because oftentimes the calculator will say that that's 5 point something, something, something. That's not what I mean. All right, that would be approximating it. So a nice simple rule of thumb is that simplify answers usually don't contain decimal points, and they often do still contain radicals, okay? Because what it means to simplify a radical is to use the product rule to make the radicand as small as possible. Remember, the radicand is the expression inside the radical, okay? So we're going to use the product rule to simplify these radicals. So let's go back over to the tablet. Oh dear, hold on. Oh, here we go. Okay. All right, so here's how this works. Question number 1, is 27 a perfect square? And the answer is no. So the second best thing is, does 27 have any factors that are perfect squares? And if so, give me the largest one possible. Okay, the largest perfect square factor of 27. The answer is 9. Okay, so the Mitchell vocabulary that I used for this, and you know, as we get more experience with doing this, you won't see me always writing all of this out. The reason the 9 is here is because it is a perfect square. And what I call this number 3, I call it a leftover. Okay. A leftover is a factor that has no perfect square factors. Now I'm going to use the product rule to pull this apart into 2 separate radicals. So according to the product rule, this is the square root of 9 times the square root of 3. And now I will evaluate the square root of the perfect square. That comes out to 3. And then you just leave this as square root of 3. So that's what I mean by simplify. We have reduced the radicand all the way down to 3, which is as small as it gets. And we've got this 3 sitting outside. Okay. Letter B, it's the same idea, except with a cube root. So question number 1, is 108 a perfect cube? And you might have to think about that for a few extra seconds. What are my first few perfect cubes? Well, they're 1, 8, 27, 64, and then the next one is 125. Okay. So the answer is no. All right, so then the next question is, what is the largest perfect cube factor of 108? And please, please, please feel free to use the calculator to help you with this. Okay, out of the numbers on that list, and the 1 is not going to help. So really, there's only 3 numbers there you have to try, right? It turns out that 27 is a factor of 108 because 108 is 27 times 4. Okay, so this is my perfect cube. This is my leftover. All right, so according to the product rule, that's equal to the cube root of 27 times the cube root of 4. The cube root of 27 is 3. So the simplified form of this is 3 times the cube root of 4. All right, next. The square root of 64y to the 9th. So now we're throwing the alphabet into the mix. So we need to figure out what is our perfect square and what is our leftover. Well, in this case, the whole entire 64 is going to go in the perfect square category. So now I just have to decide what to do with the y to the 9th. Well, I claim to you that y to the 9th is not a perfect square but y to the 8th is. Why is y to the 8th a perfect square? Well, it's because, a little thought bubble over here. The square root of y to the 8th would be y to the 4th, wouldn't it? And that's because the square of y to the 4th is y to the 8th. All right, so you put your y to the 8th with the perfect squares, makes your leftover a y. Break that into two separate radicals. Square root of 64y to the 8th times the square root of y. The square root of 64y to the 8th is 8y to the 4th. And then you put the square root of y over here. This would be one of those situations, remember in, can't remember if it was the last section or the one before, I warned you to be careful about how you put these answers in your online homework. So this would be a situation, again, I mean 8y to the 4th times the square root of y. So you would get the y to the 4th by using the exponent button, and you would get the square root by using the square root button. I'm pretty sure square root has a separate button from nth root, if I remember correctly. All right, we wouldn't want to get that mixed up with 8y times the 4th root of y. All right, and whenever I write them with a pen, I try to make it very, very clear which one I mean, but that's not as easy to do on the computer. All right, and the last example in this batch, we're going to simplify the 5th root of negative 243z to the 9th. So this is where you might want to go to your, I'm calling it a handout. It was really a slide in the, it was in 10.1 with all of your perfect nth powers less than 1,000. 243 was on that list under 5th powers. All right, and so I'm just going to tell you that the 5th root of negative 3, I mean the 5th power of negative 3, I'm sorry, is negative 243. So for that reason, put a line here. Negative 243 is a perfect 5th power. So it's going to go in the perfect 5th power group. Now, how do you suppose I'm going to break up that z to the 9th? Should I do the same thing I did when it was a square root and break it into z to the 8th times z? Well, no, I'm not going to do that because this is a 5th root, so that's different. The biggest perfect 5th power factor of z to the 9th is actually z to the 5th, which would make my leftover z to the 4th. Okay. And now when I break that into two separate radicals, I get the 5th root of negative 243z to the 5th times the 5th root of z to the 4th. So the simplified form of this would be the 5th root of negative 243z to the 5th, which is negative 3z. And that's times the 5th root of z to the 4th. See the difference between how I wrote this answer and how I wrote this answer? All right, in the top answer, the little 4 is an exponent, and in the bottom answer, the little 5 is an index. So I try to make it very clear that the little 5 goes with the radical, and when you're putting this answer in your online homework, you would need to use this button. All right. So going back to the presentation. Whoops. Okay, one last example under simplifying. We're going to use the quotient rule to divide and then simplify if possible. All right, so back to the tablet. All right, first thing we have is 7 times the 4th root of 162 divided by the 4th root of 2. So according to the quotient rule, the 4th root of 162 divided by the 4th root of 2 is equal to the 4th root of 162 over 2. And the reason that's helpful is because it just so happens that the 4th root, I'm sorry, that 162 divided by 2 is 81. It's almost as if somebody rigged this. Spoiler alert, they rigged it. All right. The 4th root of 81 is 3. So believe it or not, that big nasty expression just comes out to 21. All right. And then a similar example with square root. This might be a good one for you to pause the video and try yourself. All right, just be careful with that 5 on the bottom. All right, the 5 on the bottom is really a 1 over 5. All right, the difference between that and what's on top is if you put a 1 here, then you can think of that as 7 over 1. Down here, the 1 would go there and it would make the coefficient 1/5. Okay. And by the quotient rule, the radical part is equal to the square root of 270y squared over 3y to the negative 4. All right, so now let's simplify the expression under the radical. 270 divided by 3 is 90. And y squared divided by y to the 4th, that would be y to the power 2 minus negative 4, which is 6, right? Okay, I'm not sure I have enough room to finish this problem. I might need to erase letter A. You know what? Let's go ahead and do that. Okay. There we go. Now we got plenty of room. All right, square root of 90y to the 6th. We need to break that into perfect squares and leftovers because even though y to the 6th is a perfect square, 90 is not a perfect square. However, it does have a perfect square factor. It has a factor 9. So let's put 9y to the 6th over here. We'll put 10 over there. Break that into 2 radicals. And by the way, if you're comfortable, you can skip this next step. I'm leaving it in because it's still kind of new. The square root of 9y to the 6th is 3y to the 3rd. Okay. Now, if you were doing this for me, I suppose you could leave your answer like that. And your online homework probably won't be too picky. But if I was trying to pretty it up, I would probably write it like this: 3y to the 3rd, square root of 10 over 5. That's probably how I would write that.